On the morning of April 12, 1999, on the campus of MIT, Professor Michael Dertouzos held the attention of some of computing's finest minds as he described the motivation and aspirations for a major new research project. He pulled no punches in expressing frustration with the previous 40 years of computing.
We have focused on designing for machines. We put little envelopes, we call them operating systems, we call them browsers, we call them network software. And then we throw all this stuff at the user. Ladies and gentlemen, this must stop.
The gauntlet was down, and this challenge would, over the next 5 years, literally change the landscape of computing research at MIT, energizing hundreds of faculty, students, researchers, and industry partners toward a new vision of pervasive, human-centered computing. They called the project Oxygen. As Project Oxygen got underway in 2000, it soon became clear what areas needed work in order to realize Dertouzos' challenge of doing more by doing less. Human-like interfaces would make it easier to summon the computing power from devices and the walls. New ways of pinpointing position could make location-based services possible. A new computing architecture could make devices able to morph their function on the fly. New software architectures would adapt to changing resources as people and devices move from place to place. New security methods would protect the integrity of mobile devices and networks. And new collaboration technologies would create new ways of working together. Taking those concepts from whiteboard to reality would pose tough new challenges to the MIT community and has been a key catalyst for merging the Artificial Intelligence Lab and the Lab for Computer Science, bringing them together in the new Stata Center at MIT. The most visible challenge would be that of creating interfaces to machines, interfaces that feel natural to humans.
Work that we're doing here is really focusing on conversational interaction, so that goes far beyond just speech recognition.
Dialogue modeling is perhaps the hardest part of this process of being able to sort of present the machine side of the conversation. And eventually the information needs to be turned into phrases and sentences through natural language generation, and ultimately through speech synthesis so that you can speak those words.
We built some really interesting technology for tracking the human body and allowing gestural interaction with virtual environments and through conversation.
We've illustrated the possibility of understanding informal hand-drawn sketches in a number of domains, including mechanical engineering and software engineering. We've done some of the early work in multimodal integration. You can sketch and talk in simple ways about the thing that you're drawing.
To support a nomadic lifestyle with ubiquitous computing, mobile devices would need to know exactly where they are and even which way they were facing, both indoors and out. MIT teams came up with Cricket, which could ascertain location of people and devices within a few centimeters.
Cricket is not the first indoor location system, and I highly doubt that it will be the last one. But I think that its main contributions are in a rather unique way of thinking of the problem, in that if you're interested in a system that scales well with a large number of users, that provides a high degree of accuracy to within a few centimeters, that is implementable and has been implemented in a small form factor, and you're interested in preserving user privacy, Cricket might be the right technology.
Mobile devices would need to become radically more flexible in order to process streams of audio, visual, and other data in different ways at different times. This opened the door for a new kind of chip design, the raw chip, that would enable a device to adapt to the needs of the moment.
Depending on the needs of the user, the handheld would need to turn itself into a radio or a cell phone or a video player, or for that matter into some kind of a camera. Now in the past, these devices might have held customized chips to do that task. The technology we had to create was a way for those wires to be able to be programmed at runtime in software.
Several Oxygen projects have been working on the infrastructure that connects the devices and the environment. all focused on the best possible way to accomplish what the user really wants to do.
The approach that we're taking is to have some formal representation not only of the implementation choices that have been made, the fact that we're using this input device and that output device and so on, but the higher level goal that caused us to make those implementation choices.
We've gotten to the point where we can actually federate a lot of these technologies and get them to work together, cooperatively, to build some larger set of capabilities.
With so much computing available in the walls and flexible, adaptable devices becoming more common, it would become absolutely critical to be able to identify and authenticate these devices. These security issues led to the discovery of an innovative method of fingerprinting seemingly identical devices.
Sort of the eureka moment was, gee, why don't we let the device itself act as the key? Each device has an electronic circuit in it. These electronic circuits are different if you look at them from a microscopic standpoint because they've all been fabricated a little bit differently. So if we could extract sort of a fingerprint from each of these different devices, then we could extract keys from those fingerprints.
Walk anywhere within the Stata Center today, and you'll see Oxygen collaboration experiments at work. Interactive kiosks that not only give directions, but also download guiding pictures to a cell phone. An enormous microphone array that can pick a single voice out of the babble of a crowd. An intelligent conference room that can respond to the gestures and commands of meeting participants. These researchers and students are not only creating new technology, but they're living with it as well. It may look like a 9-story playground, but it's really a proving ground for new ideas in pervasive computing.
One of the things that really made Project Oxygen work was having a number of companies working with us.
They brought in a really good feedback mechanism as to what was important to industry.
The researchers at MIT were creating the world of the future. They lived the technologies that we want to create, and experiencing it then gives us a better understanding of what the real problems are that we need to address, what the real benefits are going to be by that technology.
At Delta Electronics showroom, they actually have something called the Future Home, in which you can actually speak to the room and be able to control various appliances and be able to make use of the computations and communication capabilities around you.
Our interaction with MIT professors gave us insight into future trends and next generation technologies.
In the past 4 or 5 years, we have been sending engineers to Boston working with Csail on oxygen-related projects, and the results were very good. We plan to join the next phase of Oxygen project.
If the theme of the first 5 years of Project Oxygen was Let 1,000 Flowers Bloom, the next 5 years will be Make It Real, applying these technologies to application areas outside the academic setting.
There are still tremendous challenges in a wide range of areas facing us. Things like environmental robustness, individual speaker characteristics.
A speech-based interface simply cannot stand by itself. We need to, just like in human communication, we need to incorporate other modalities.
One of our important next steps will be to do a number of user studies to see how people will actually interact with this kind of technology and to try putting it into a number of real-world application domains.
There's progress to be made both in miniaturizing and simplifying the current architecture so that it's something you can just really set up without any effort in a meeting room or in every office in this building. And also connect it in a deep way with understanding and meaning.
Hopefully in phase 2, perhaps it can understand human emotion as well and include human emotion in its services.
What does it take for your grandmother to use this technology or be able to interact with her devices in her house in a manner that she can understand?
We hope that Oxygen 2 can be sort of a place where the technology providers can come together with the service providers and they can cross-fertilize through us as developing the appropriate technologies on each side in new ways that by themselves no one may have imagined.
How can technology help you live independently longer and live productively longer.
Healthcare, education, financial services, engineering design, home entertainment. These are just a few of the application areas where Project Oxygen will begin to get its real-world test over the next 5 years. This leads to one ultimate measure of success.
One measure of our success would be if a group of users are actually using our technologies and living their day-to-day lives under the aegis of our technologies.